Hello, it's Stat 134, Lecture 12. Last time we did Markov's inequality in section 3.2, which says that if you have a non-negative random variable, then the probability of being in the tail, in the right tail, is the expectation of x over a for every a. So, for example, is it possible that half of U.S. flights have delay times greater than 3 or more times the national average? The answer is no. If you apply Markov with a 3 times the expectation of x, you'll see that the most that that flight delays could be 3 times greater than 3 times the national average is 1/3. So 1/2 is too big. Today we're going to look at the expectation of several variables and then talk about SD invariance in section 3.3 as well as Chebyshev's inequality. To increase our repertoire of random variables, the geometric random variable is the number of trials until your first success. For example, if x is the number of p coin tosses until your first heads, for example, you could throw a head, which would be x is 1 and probability p, or you could throw a tail and then a head, which is x is 2, probability qp, and so on. You get the geometric formula, probability x is k is q to the k minus 1 p. So now, on to section 3.2, expectation of a function of a random variable. So here is the definition of expectation, which is a weighted average of the values of x by the probability that x is x. So the definition for the expectation of a function of a random variable is very similar, except instead of x, we have g of x. If you think about it, it seems a little strange. Let's make sure we understand it. So look at an example where x has two values, 1 and minus 1, with probability 1/4 and 3/4. And g of x is just x squared, which maps 1 and minus 1 to 1. So it maps, so y is 1 with probability 1 here. If you were to find the expectation of y just using the definition of expectation of y, it would be 1 times the probability that y is 1, which is just 1 times 1, or 1. But you could also say that, hey, you know what? The probability that y is 1 is the same as the probability that x is 1 plus the probability that x is minus 1, because 1 and minus 1 map to y is 1. So essentially what we're doing here is we're writing the expectation as a larger sum, where we're summing over all the different values of x instead of all the different values of y. The values of x, there will be more values of x possibly than y if your function g isn't 1, 1. So let's take a look at an example here. Suppose a random variable x has geometric p distribution on 1, 2, 3, and so on. Let p be greater than 2/3. Find the expectation of 3 to the power x. If you use an infinite sum, you must simplify it. So we're going to use the fact that, so we're going to use our geometric formula as well as the definition for the expectation of g of x. And we see that the expectation of 3 to the power x is this infinite sum indeed. And we can write it out and see that it is in fact 3p times a geometric sum. And 3q is less than 1 because p is greater than 2/3. So that allows us to write that infinite sum as 1 over 1 minus 3q. So we get 3p times 1 over 1 minus 3q. Just a heads up, make sure you know your geometric sum formula. So now let's say that we have several variables. So x and y joint distribution. So the formula for the expectation of a function of two variables is very much the same as for one variable. Let's just take a look at this in an example. So say that xy is a joint distribution where x takes the values 0 and 1, and y takes the values 0, 1, and 2. If you think of x as actually a function of x and y, namely g of x, y is just x, then we can apply our formula for expectation of g of x, y, and we get, we're going to sum over all the x's and y's, so we're summing over all of the 6 cells that we have here. And so we have, when x is 0, we have 0 times a quarter plus 0 times a quarter plus 0 times 0. And then we have x is 1, and so we have 1 times 0 plus 1 times a quarter plus 1 times a quarter. So adding that all up, you get a half, which is exactly the same as what you would get if you just used the marginal probability for x. So we know that 0 has marginal probability 1/2, and x has probability 1/2. So that gives you the same expectation. And so using our formula for the expectation of a function of 2 variables, we can show that the expectation of x plus y is the expectation of x plus the expectation of y, and we can also show that the expectation of xy is equal to the expectation of x times the expectation of y. Just be very aware that the first theorem here doesn't require any independence, whereas the second one does. In the second formula here, notice where we use independence. It's to factorize the joint distribution here. We are done with section 3.2, on to 3.3 on standard deviation. The standard deviation is the average spread of your data around the mean. So for example, if you look at this distribution here, is the average spread around the mean 5, 15, or 50? You guessed it right, it's 15. How can I tell? Well, I'm going to look at the center of my data, which is 35, and it looks like most of my data is within 10 of that, right? If you look, it seems to have a peak around 25. I would say, most of your data is going to be around 35, but there are some data points further away. So 10 plus a little bit more is going to be, let's say, 15. Certainly not going to be 50. That would be a very, very broad distribution. Certainly not going to be 5. That would be a very pointy distribution. 15 is just right. So the definition of the standard deviation of x, we start with the deviation, so x minus the expectation of x. What we really want is we want the average of the absolute value of that deviation. But absolute value isn't friendly with calculus. So instead we're going to square x minus expectation of x, then take the expectation of that, and to get the units right, we need to then take the square root to undo that square that we did earlier. The variance is just the square of the SD. So on to Chebyshev's inequality. So Chebyshev's inequality applies to any random variable x, but you do need to know both the expectation of x and the SD of x. And it says that to be more than k SDs away from the mean, the chance of that is less than or equal to 1 over k squared. So Chebyshev's inequality also provides a tail bound. And so, for example, if you wanted to find what's the probability that x is more than 30 away from 35, well, I would notice that okay, 1, 35 is the average, and 2, 30 is 2 SDs. So k is 2 here, and I can apply Chebyshev. To get that probability is less than or equal to a quarter. So what can you say about the probability that x is greater than or equal to 65? Well, this distribution isn't symmetric, so you really can't say any more than that it's less than or equal to a quarter. If the distribution was if the distribution was symmetric, then you could say that it's less than or equal to an eighth, but that's not the case here. So let's just review. Markov requires x to be non-negative. You need the expectation of x, and it's about the right tail. Chebyshev is good for any x. You need both the expectation and the SD, and it can apply to one or both tails. So then we did a concept test that I might have made a little bit too easy, but that's okay. The last one was probably too hard, so it all balances out, right? A list of incomes has an average of 70,000 and an SD of 30,000. Let P be the proportion of incomes over 100K. To get an upper bound for P, you should not apply normal distribution because our incomes isn't normal. Markov works because incomes is non-negative, and that would give me a bound of 70 over 100. Chebyshev would work, but isn't really useful here because I see that my K is 1, and if K is 1, then the bound I get is 1. And the probability being less than or equal to 1 isn't helpful. So the answer would be B. We then finished with a proof of Chebyshev. Chebyshev follows directly from Markov's inequality, but you do need the SD. So the key here is that you let y be the deviation squared, which is a non-negative random variable, and you let a be k squared variance of x. So then applying Markov, we see that the expectation of y is precisely the variance of x. So we get the variance of x over k squared variance of x, and a beautiful thing happens. The variance of x is canceled, and we get 1 over k squared. Awesome. Furthermore, y greater than or equal to a translates to what I've written here, which when you take the square root of both sides of this inequality, you get exactly the probability that the absolute value of x minus expectation of x is greater than or equal to k STX. It is all beautiful. So that gives us Chebyshev's inequality. So that's the show on this Wednesday. I hope you enjoyed it, and I look forward to seeing you all on Friday.